Okay, think about workplace safety for a second.
Yeah.
We often picture hard hats, maybe safety vests, right?
Standard stuff. Yeah.
But get this. Some experts, they actually consider ensuring safety in areas where explosions could happen as, well, one of the toughest nuts to crack in the whole field.
Mm-hmm.
It's just a completely different level of complexity.
Oh, absolutely.
Yeah.
And for really good reason. I mean, we're not just trying to avoid someone slipping on a wet floor.
Right.
We're talking about preventing something incredibly fast, incredibly powerful,
Yeah.
an explosion. And that means, well, you have to get down into the nitty-gritty, the technical side, the chemical principles.
And that's exactly what we're diving into today.
Spot on.
Exactly. So we've got our hands on this really comprehensive guide. It's all about ATEX.
ATEX, right.
Now, ATEX is short for explosive atmospheres, and it's basically the EU's framework for tackling this exact issue. It lays out, the laws and the technical know-how.
How to actually prevent these things in industrial settings.
Yes. And this document, it covers everything. The ATEX rules themselves, figuring out the risks, how to pick the right equipment, putting preventative measures in place. It's all in there.
So our mission then for this deep dive, it's to take this, well, mountain of information.
It kind of feels like it.
Yeah. And pull out the really essential knowledge. What do you really need to understand to handle explosive atmospheres safely?
Right. We want to pinpoint the core ideas, maybe even uncover some surprising facts, but, without getting totally lost in the jargon.
Keep it understandable, yeah.
Okay, let's start unpacking this then. To even think about stopping explosions, we first need to understand, well, what causes them in the first place? Our guide kicks off with something called the fire triangle.
Ah, yes, the fire triangle.
Classic.
You need three things.
Fuel.
Something that burns.
Right. Then air, or more specifically, the oxygen in the air.
Got it.
And finally, an ignition source. Something hot enough or energetic enough to get it started.
Okay, fuel, air, ignition. It's a simple idea, but it's fundamental. If you can reliably take away just one of those three things, poof, no fire, no explosion, you eliminate the hazard.
That makes a lot of sense. Simple but powerful. And our source, it gives a very specific definition of an explosive atmosphere. It's not just like any flammable stuff floating around.
No, exactly. The definition is quite precise. It's a mixture of flammable substances, could be gases, vapors, mists, even certain types of dust mixed with air.
Okay.
But only under specific atmospheric conditions. And if those conditions are met and you introduce an ignition source, then the combustion can spread really rapidly through the entire unburned mixture. That's the explosion.
Right, that rapid spread. And what exactly are these atmospheric conditions we need to watch out for?
Well, according to the guy, we're generally talking about a pressure range of about 0.8 up to 1.1 bar absolute.
Okay, near normal atmospheric pressure.
Pretty much. Yeah. And a temperature range usually between minus 20 degrees Celsius and plus 60 degrees Celsius.
So not extreme conditions typically.
Not usually, no. If things are way outside that window, the specific ATEX rules we're digging into here generally don't apply directly. Other safety measures might, but not these specific ones.
Interesting detail. So it's a defined zone of pressure and temp. Now, the guide also makes a point of separating hazard from risk. Can you break that down for us? It sounds important.
It really is. Think of it like this. A hazard is the potential for harm. So having a flammable atmosphere present, that's a hazard. Having a potential ignition source nearby, also a hazard.
Okay, the potential exists.
Right. Risk, on the other hand, brings in the likelihood. How likely is it that this flammable atmosphere will actually ignite? And if it does, how severe will the consequences be?
So it's about probability and severity.
Exactly. You might have a hazard present, maybe a zone 2 area where an explosive atmosphere is unlikely but possible. But if the chance of an effective ignition source being there at the same time is extremely low, then the overall risk might be considered acceptable, or at least manageable.
Okay, that distinction is key. Hazard is the potential. Risk is the probability and impact.
Got it. So now we have the basics. The guide really hammers home that prevention, stopping these explosive atmospheres from even forming, is the #1 priority. Why is that so critical?
Well, because it's the most effective way to eliminate the risk completely. It's just logical, right?
Yeah.
If there's no flammable atmosphere, it doesn't matter if you've got sparks flying around or hot surfaces, there's simply nothing to ignite.
You cut it off at the source.
Exactly. You're nipping the problem in the bud before it even becomes a serious possibility.
Okay. And our source outlines, I think, 4 main ways to achieve this prevention.
Yeah.
What are those?
Right. 4 key methods. The first one, maybe the most obvious, is just avoid using flammable materials altogether if you possibly can. Switch to something non-flammable.
Sometimes possible, sometimes not, I guess.
Exactly. The second method is to control the concentration. If you do have flammable substances, you make sure their concentration in the air stays well outside the explosive range. So either too little fuel or too much fuel.
Precisely. Keep it below the lower explosive limit, the LEL that's too lean to burn, or keep it above the upper explosive limit, the UEL that's too rich, not enough oxygen mixed in.
The LEL and UEL, so those are like the boundaries of the danger zone, yeah?
That's a great way to put it. Below LEL, not enough fuel. Above UEL, not enough oxygen. Bang in the middle. That's where the danger lies.
But the guide warns this can be tricky, relying on staying outside the limits.
It can be, yeah,
Mm-hmm.
because process conditions can fluctuate unexpectedly. You might think you're safely below the LEL, but a small change could push you into the flammable range. So it needs careful monitoring.
Okay. What's the third method?
The third method is inerting.
Inerting. Sounds like you're making the atmosphere inactive, unable to react.
That's exactly it. Inerting means you deliberately reduce the oxygen concentration in the atmosphere by replacing some of the air with an inert gas.
Like nitrogen
Yeah.
or carbon dioxide.
Those are the most common ones, yes. Since oxygen is crucial for the fire triangle, if you lower its percentage enough, you make ignition impossible, even if fuel and an ignition source are present.
You're taking away the air part of the triangle.
Effectively, yes. You're reducing the oxygen below the level needed for combustion.
Okay, and our guide looks at both CO2 and nitrogen for this. Let's start with carbon dioxide. What are the key things to know about using CO2 for inerting?
Well, the guide points out CO2 is relatively inert, meaning it doesn't react much with most common stuff. It's already in the air, just in tiny amounts.
Right.
One thing to watch out for, though, is if moisture is present. CO2 and water can form carbonic acid, which can be corrosive over time.
Okay, good point. And how is it usually stored?
Typically, as a liquid under pressure, you might have big refrigerated low-pressure storage tanks or sometimes smaller high-pressure cryogenic cylinders.
And the guide gives a practical example of CO2 inerting.
Yeah, a good one is in coal grinding facilities, like you find in cement plants. During normal operation, they might use waste gases to keep things inert.
Okay.
But during shutdown or startup of the coal mill, those are high-risk periods for dust explosions or smoldering fires. So injecting an inert gas like CO2 is often used as an extra safety measure during those specific times.
Makes sense. Those transitions start-stop often seem riskier. What about the practical side of using CO2? Like how much can you actually deliver?
Yeah, the guide mentions that your delivery capacity, how much CO2 gas you can get out, mainly depends on the size of the vaporizer, the bit that turns the liquid into gas.
And the ambient temperature.
And the ambient temperature, exactly. Colder weather can reduce the vaporization rate. It also notes that while low-pressure systems might seem like they'd use more energy for cooling, they're often preferred for larger-scale needs, especially in warmer climates, because they can offer higher discharge rates.
Interesting trade-offs. Okay, so CO2 is one option. What about nitrogen? The guide also talks about N2 for inerting.
Yep, nitrogen makes up about 78% of the air we breathe, right? And it's non-combustible.
Very inert.
Very. It's usually stored at high pressures, often as a liquid. And the guide flags a really, really critical safety point with liquid nitrogen.
Oh, what's that?
When liquid nitrogen turns into a gas, it expands massively. We're talking about a volume increase of around 700 times.
Wow, 700 times.
Yeah. So even a small leak of liquid nitrogen can very quickly displace all the oxygen in an enclosed space. It creates an asphyxiation hazard.
So while it prevents the explosion hazard from the flammable material?
It can create a life hazard for anyone in the area. Lack of oxygen. So ventilation and monitoring for oxygen levels are absolutely crucial if you're using nitrogen inerting.
A very serious consideration. And when might you choose nitrogen over CO2?
The guide suggests it's often used in situations where getting a consistent, reliable supply of CO2 might be difficult or impractical.
Okay, so prevention is plan A. Avoid the material, control the concentration, or inert the atmosphere. But the guide also admits that sometimes you just can't completely prevent an explosive atmosphere from forming. What happens then?
Right. Sometimes the process inherently creates the risk. In those cases, we have to move to mitigating measures. If we can't eliminate the possibility of an explosion entirely, we need strategies to minimize the damage if one does occur.
Backup plans.
Essentially, yes. The guide outlines 4 main categories for these mitigating measures.
All right, lay them on us. What are the options when prevention isn't foolproof?
Okay, first up is explosion relief venting. This involves designing specific weak points, often panels or membranes, into the equipment.
Like predetermined breaking point.
Exactly. They're designed to burst open safely at a certain pressure if an explosion starts inside. This allows the pressure, the flame front, and any unburnt material to escape to a safe location, usually outdoors.
So it limits the pressure buildup inside the equipment itself.
Precisely. It gives the explosion a controlled escape route, preventing the equipment from rupturing catastrophically.
But you mentioned venting it safely. What about the, fireball and pressure wave coming out of the vent?
That's a huge consideration. The guide stresses this. You absolutely have to account for the effects outside the vent, the flame jet, the pressure wave. You need a clear, safe discharge area. And you have to consider any potentially toxic materials being released.
Right, can't just vent toxic dust anywhere.
Definitely not. The guide even touches on the calculations involved in sizing these vents, especially for dust explosions. You need to know things like the dust's case value, how strong the explosion could be, the maximum pressure the vessel can take, the vessel volume. It's proper engineering.
Sounds complex. Okay, what's the second mitigation category?
The second is explosion-resistant design, sometimes called explosion containment.
So instead of venting it, you just build the equipment super strong.
That's the idea. You design and build the equipment robustly enough to withstand the maximum pressure generated by an internal explosion without rupturing. It might deform slightly, but it contains the blast.
Makes sense. When would you use this?
It's often more practical and economical for smaller volume equipment, where the cost and weight of making it that strong aren't prohibitive. Trying to contain an explosion in a massive silo, for example, would be extremely difficult.
Okay, build it strong enough. What's number 3?
Number 3 is explosion suppression. This is a more active system.
Active? How so?
It uses very fast-acting detectors, pressure sensors, or optical flame detectors to sense the very beginning of an explosion, like within milliseconds.
Wow, that fast?
Yeah, it has to be. As soon as it detects the initial pressure rise or flame, it triggers the rapid injection of an extinguishing agent, like a dry chemical powder, or even water mist directly into the vessel.
So it snuffs out the explosion before it really gets going.
Exactly. It stops the flame propagation and limits the pressure rise. It's like hitting the emergency brakes on the explosion itself.
That's clever. When is suppression a good choice?
It's particularly useful where venting isn't practical. Maybe the equipment is indoors, or you're handling toxic materials that you absolutely cannot release, or where containment would be too costly.
Okay, suppression. And the final category.
The final one is explosion isolation.
Isolation, stopping it from spreading.
Precisely. If you have interconnected equipment like ductwork connecting vessels or conveyors moving material between them, an explosion starting in one part could potentially travel and trigger secondary, maybe even more violent explosions elsewhere.
Ah, a chain reaction.
Right. Isolation aims to prevent that. It uses devices to block the flame and pressure propagation. Things like quick-acting shutoff valves or flame arresters.
Flame arresters, what are they?
They're like special meshes or filters. They let normal process gas flow through, but they quench a flame front trying to pass. Other methods include rotary valves, which act as a physical barrier for dusts, or even just ensuring you have a sufficient choke of material in a screw conveyor to stop flame passage.
Okay, so stopping the explosion from traveling, venting, containment, suppression, isolation. 4 key ways to mitigate. These sound absolutely vital if an explosion does kick off.
They really are. They're about limiting the consequences.
Now, the guide then gets, well, even more technical. It delves into flammable limits and ignition properties. This sounds like the real deep science behind it all.
It is, and understanding these parameters is absolutely fundamental for doing those risk assessments properly and choosing the right safety measures, including the right equipment.
Okay, so we revisit LEL and UAL, the lower and upper explosive limits. What more do we learn here?
We dig a bit deeper. As we said, they define the concentration range where ignition is possible. But the guide emphasizes these aren't fixed constants. They can change, primarily with temperature and pressure.
How so?
Generally, higher temperatures and higher pressures tend to widen the flammable range. They might lower the LEL slightly and raise the UEL, meaning there's a broader range of concentrations that can ignite.
Making ignition easier, essentially.
Correct. The LEL in particular is a really critical value used when defining those hazardous zones we'll talk about later.
Okay. Then there's the auto-ignition temperature, or TIG. What's the key takeaway there?
The TIG is the lowest temperature at which a flammable mixture will spontaneously ignite just from the heat of its surroundings, without any spark or flame, just heat alone.
Okay, self-ignition.
Exactly. And the really important point the guide makes is that this value isn't absolute. It can vary significantly depending on how it's measured, the size and shape of the container, even the type of surface the mixture is in contact with.
So it's context dependent.
Very much so.
Okay.
And this directly links to those temperature class codes you see on ATEX equipment T1 down to T6.
Ah, the T ratings.
Yes. That T rating tells you the maximum surface temperature the equipment will reach during operation under fault conditions, including a safety margin. It ensures the equipment itself won't get hot enough to reach the auto-ignition temperature of the surrounding atmosphere.
So T6 rating means a lower maximum surface temperature than T1, right? Safer for more easily ignited gases.
Precisely. T6 is the coolest, safest rating, suitable for gases with low auto-ignition temperatures. T1 is the hottest. You have to match the equipment's T rating to the TIG of the specific gas or vapor present.
Got it. Then we have gas groups, IIA, IIB, and IIC. What determines these groupings?
These groups categorize gases and vapors based on how easily they can be ignited, specifically by sparks or flames. It relates to their minimum ignition energy, MIE, or something called the maximum experimental safe gap, MESG.
Okay, simpler terms.
Think of it like this. Some gases need only a tiny spark to ignite, while others need a much bigger one. Group II contains the most easily ignited gases, like hydrogen and acetylene. They need the least energy.
So they require the highest level of protection.
Exactly. Equipment rated for II offers the most stringent protection against spark ignition. Then comes IIB, like ethylene, and finally IIA, like propane or methane, which are relatively harder to ignite by spark.
And the equipment has to be compatible.
Yes. Equipment marked IS can be used for IIB and IIA atmospheres. IIB can be used for IIA, but you can't use IIA equipment in an IIB or IIC atmosphere. The equipment's rating must be suitable for, or better than, the gas group requires.
Okay, like a hierarchy of protection. The guide also mentions vapor density briefly. Why is that relevant?
Vapor density, how heavy a gas or vapor is compared to air, doesn't directly measure flammability, but it's really important for hazardous area classification.
Because it determines where the gas might go.
Exactly. Heavier than air vapors, like propane or gasoline vapor, will tend to sink and collect in low spots, pits, trenches. Lighter than air gases, like hydrogen or methane, will rise and collect near ceilings or in roof spaces. Knowing this helps you predict where the hazardous atmosphere is likely to be.
But the guide adds a caveat.
Yes, it warns that relief conditions can affect density. For instance, a gas released under high pressure can cool significantly as it expands, making it temporarily denser than it would normally be at ambient temperature. So you need to consider the release dynamics too.
Good point. Okay, that covers gases and vapors pretty well. Now, what about dusts? The guide highlights some key differences when dealing with explosive dusts.
Yes, dust explosions have their own distinct characteristics and parameters. The very first step, actually, is determining if the dust is combustible at all. There are standard tests that classify dusts into Group A, combustible, or Group B, may burn, but doesn't readily propagate flame.
So first, can it even explode?
Pretty much. Then, similar to gases, dust clouds have a lower explosive limit, LEL. It's the minimum concentration of dust suspended in air needed for an explosion.
What sort of concentrations are we talking about?
Typically, it's in the range of 20 to 60 grams of dust per cubic meter of air, although some can be higher. The guide gives a really striking visual for this.
Oh, yeah.
It says a coal dust cloud at just 40 GeoNodes would be so dense you wouldn't be able to see a standard 25-watt light bulb from only 2 meters away.
Wow, that's thick. So you don't need much dust to be in the danger zone.
Not necessarily, no. Interestingly, unlike gases, the upper explosive limit, UEL, isn't generally considered a practical safety parameter for dusts. It's usually very high and hard to reach or maintain. The focus is almost entirely on the LEL and preventing ignitable clouds from forming.
Okay. What about how easily dusts ignite? Is there an equivalent to the gas groups?
Not exactly groups, but a key parameter is the minimum ignition energy, or MIE. This measures how sensitive a dust cloud is to ignition by an electrical spark.
And why is MIE so important?
It's absolutely crucial when assessing risks from static electricity discharges and also from potential mechanical sparks. If a dust has a very low MIE, even a tiny static spark that you might not even feel could be enough to set off an explosion.
And how much variation is there in MIE for dusts?
It's enormous.
Yeah.
The guide says the range can span at least 8 orders of magnitude.
8? That's huge.
It is. You have some dusts like fine sulfur or certain metal powders with MIEs down in the single millijoules range, incredibly sensitive. Then you have others, like maybe some food products or cooler dusts that might need thousands of millijoules. The guide gives examples like calcium stearate needing maybe 10 millij, while something like sewage sludge could need over 10,000 millij.
So you really need to know the MIE of the specific dust you're handling.
Absolutely. It dictates the level of precaution needed, especially regarding static control.
What about ignition temperatures for dusts? Is it just like TIG for gases?
There are actually two main ignition temperatures for dusts you need to worry about. First is the minimum ignition temperature, MIT, of a dust cloud. That's similar to the auto-ignition temperature for gases, the lowest temperature of a hot surface that can ignite a dust cloud floating past it.
Okay, MIT for the cloud. What's the second one?
The second is the layer ignition temperature, or LIT. This is the lowest temperature of a hot surface that can cause a layer of dust settled on that surface to start smoldering or glowing.
Ah, so
Yep.
dust just sitting on hot equipment.
Exactly. And this is really important because that smoldering layer can then act as a potent ignition source for a dust cloud if the dust gets disturbed. The LIT is typically measured for a 5 mm thick layer, and the guide notes that the dust's thermal history, if it's been heated before, can affect this value.
So MIT for clouds, LIT for layers, both important.
Both critical for setting maximum surface temperature limits for equipment used in dusty areas, again with safety margins applied.
Okay. The guide also mentions something called the explosion constant, CREST and St. classes.
Yeah.
What are those measuring?
CREST is all about the severity of a potential dust explosion. It's a measure of the maximum rate of pressure rise during a standardized explosion test in a sphere. Basically, it tells you how fast and powerful the explosion could be.
So a higher CREST means a bigger bang.
A much faster, more violent pressure rise, yes. Based on the CREST value, dusts are categorized into St. classes. St. 0 means non-explosive. St. 1 is a weak explosion. St. 2 is strong, and St. 3 is a very strong explosion.
And why do we need to know this?
It's absolutely vital for designing those protective measures like explosion relief vents or suppression systems. A dust with a high cost, like St. 2 or St. 3, common for metal dusts or fine organic dust, will require much larger vents or faster-acting suppression systems than in St. 1 dust. The guide gives examples. Aluminum powder has a very high cost, whereas wood dust is typically lower, maybe St. 1 or St. 2, depending on fineness.
So cost drives the design of the mitigation measures.
Fundamentally, yes.
Finally, under dust properties, the guide mentions powder volume resistivity. How does that fit in?
Resistivity isn't about flammability or explosion severity, but it's key for assessing the risk of static electricity accumulation and discharge, especially for low MIE dusts.
Back to static.
Right, it measures how well the bulk powder conducts electricity. Highly resistive powders hold on to static charge more easily, increasing the risk of hazardous sparks. Conversely, very conductive powders allow charge to dissipate quickly if properly earthed.
So you categorize dusts based on this?
Yes. The guide mentions categories like conductive, dissipative, and non-conductive based on resistivity ranges. This helps determine appropriate handling procedures and even links to the required IP rating, dust tightness, for electrical enclosures in the area. Interestingly, it notes that truly conductive powders are rare because even metal powders often have insulating oxide layers.
And it briefly mentions North American dust groups.
Just as a point of contrast, yeah.
Right.
North America uses a different system with groups E, F, and G for dusts based on different criteria.
Okay, wow. That was a seriously detailed look at the properties that make things flammable or explosive. Now, linking all this together, the guide heavily emphasizes the critical role of risk assessment. Why is a really thorough assessment so fundamental here?
Because it's the absolute bedrock upon which all your safety decisions are built. The ATEX Workplace Directive actually legally requires employers to perform a comprehensive explosion risk assessment for any area where an explosive atmosphere might occur.
It's not optional.
Not at all. And this assessment needs to be broad. It has to look at how likely is it that an explosive atmosphere will form? How long might it stick around? What potential ignition sources are present? How likely are they to become active and effective? How might different hazards interact? And crucially, what would be the scale and effects if an explosion did happen?
So it's a really holistic view of the potential problem. And how does this risk assessment connect to those zone classifications we touched on earlier?
The likelihood and duration of the explosive atmosphere being present. Those are the direct inputs that determine the zone classification. Zone 0, 1, 2 for gas vapor. Zone 20, 21, 22 for dust. So the risk assessment informs the zoning.
Okay.
The assessment process also involves creating a detailed inventory of all flammable substances on site. You typically use the safety data sheets, the SDS or MSDS documents, to get the key properties like LEL, TIG, MIE, etc.
Gathering all the data.
Exactly. And it needs to pay special attention to specific types of equipment known to be potential problem areas, things like fans, mixers, conveyors, mills, dryers, rotary valves.
Things with moving parts, basically.
Often, yes. You need to consider factors like the speed and power of moving parts, the materials they're made from, could they generate sparks, lubrication seals, could they leak flammable material, potential temperature rises, electrostatic properties, the operating environment. It's a systematic hunt for potential hazards and ignition sources.
It sounds incredibly thorough. Now, one ignition source the guide really calls out, saying it's often overlooked, is static electricity. Why is static such a big deal in these environments?
Because it's generated so easily, often invisibly, in countless common industrial operations. And the energy released in a static spark, even a small one you might not see or feel, can be more than enough to ignite many flammable vapors and even sensitive dust clouds.
So it's sneaky and powerful.
Exactly. The guide lists numerous ways it gets generated. Particles rubbing inside chutes or pneumatic conveying lines, steam or compressed air flowing, especially if it contains droplets or particles, belts moving over pulleys, vehicles moving, even just friction between different surfaces.
Wow, it's everywhere.
It really can be. The core principle is charge separation. When materials come into contact and then separate, electrons can transfer, leaving one surface positively charged and the other negatively charged. If these charged surfaces are insulated or the materials themselves don't conduct electricity well, that charge can build up.
Until it discharges as a spark?
Until the voltage difference gets high enough to break down the air gap between the charged object and something else at a different potential, often something earthed. That breakdown is the spark.
What are some common scenarios for this charge buildup?
The guide highlights several. Liquids flowing in pipes, especially non-conductive liquids, are being poured, stirred, sprayed, or even just settling in a tank can generate charge. People walking around can build up significant charge, particularly if they have insulating footwear on an insulating floor. A person could easily generate a spark energetic enough to ignite common solvents.
Just by walking?
Yes, potentially thousands of volts. Bulk liquids filling tanks, especially if the flow is turbulent or splashing occurs, is a classic source. Powders being conveyed, sieved, or milled, the amount of charge often relates to how much work is done on the material. Handling low MIE powders in plastic containers or bags is a major concern because the plastic insulates and allows charge to accumulate on the powder. Even mists and dust clouds themselves can become highly charged.
That's a huge range of sources. So how do we control the risks from static? What are the main strategies?
The number one strategy is preventing charge accumulation by providing a path for static charges to safely dissipate or recombine before they reach dangerous levels.
Earthing, basically.
Earthing or grounding is absolutely fundamental. All conductive components, metal pipework, vessels, equipment housings, structural steel, even mobile equipment like trolleys or drums must be bonded together and connected to earth with a low resistance path.
What about things that aren't metal?
Good question. Hoses used for transferring flammable liquids or powders should be conductive or static dissipative to prevent charge buildup on the hose itself. You need to avoid isolated conductive components like a metal nozzle on a plastic pipe because they can accumulate charge and spark to an earthed object.
And people. You mentioned people getting charged.
Yes, personal earthing is crucial, especially in areas handling sensitive materials. This usually involves wearing conductive or anti-static footwear in combination with conductive flooring. The aim is to keep the person's resistance to earth low enough to prevent significant charge buildup.
Makes sense. Any other control methods?
Yes. For liquids, limiting flow rates can help prevent excessive charge generation, particularly avoiding splashing or spraying, which creates highly charged mists. For powders, minimizing the energy input during handling, like using lower conveying velocities, can reduce charging. And a key principle: where you have flammable atmospheres with low MIEs, you should strongly avoid using insulating materials, like standard plastics, for equipment construction, as they can lead to various types of hazardous static discharges. Even vessels with insulating linings need careful consideration for earthing.
So good earthing and bonding are paramount, plus careful material selection and process control. Okay, let's shift gears slightly to hazardous area classification or zoning. What's the underlying goal of this whole zoning system?
The fundamental purpose of zoning is to minimize the probability of having an explosive atmosphere and an effective ignition source present at the same time.
Matching the risk to the protection.
Exactly. By classifying areas based on the frequency and duration that a flammable atmosphere is likely to be present, you create a framework for selecting appropriately protected equipment that won't become an ignition source in that specific environment.
Okay. And the guide outlines the different zone definitions again for gases, vapors, mists, and for dusts. Can you quickly recap those?
Sure, for gases, vapors, and mists, Zone 0 is where the explosive atmosphere is present continuously for long periods or frequently. Think inside a storage tank vent. Zone 1 is where it's likely to occur in normal operation occasionally. Maybe you're on a filling point. Zone 2 is where it's unlikely in normal operation, and if it does occur, it's only for a short time, perhaps due to a small leak from a seal.
0, 1, 2, decreasing likelihood or duration.
Right. And for dusts, it's similar logic, but zones 20, 21, and 22. Zone 20 is where combustible dust cloud is present continuously, frequently, or for long periods, typically inside process equipment like mills or silos. Zone 21 is where a cloud is likely to occur occasionally during normal operation, like during bag tipping. Zone 22 is where a cloud isn't likely in normal operation, and if it happens, it's infrequent and short-lived, often associated with leaks or dust escaping enclosures.
And dust has the extra complication of layer settling.
Yes, that's a key difference. Even when the cloud disperses, the subtle layer remains a hazard, as it could be disturbed and resuspended, or it could smolder if on a hot surface, linking back to the LIT. So layer presence influences Zone 21 and 22 classification.
Okay. How does the idea of grade of release fit into zoning?
The grade of release describes the source itself, how likely it is to leak or release the flammable substance. There are 3 grades: continuous release, like vapor space in a tank; primary release, expected during normal operation, like sampling; and secondary release, not expected normally, only occurs under fault conditions, like a flange leak.
And these grades link directly to the zones.
In open, well-ventilated areas, generally yes. Continuous release typically leads to zone 0 or 20. Primary release leads to zone 1 or 21. Secondary release leads to zone 2 or 22.
But you said well-ventilated areas. Does ventilation affect the grade of release?
Ah, good point. No, ventilation does not affect the grade of release itself. The grade is purely about the source characteristics, how often it leaks. However, ventilation has a massive impact on the extent or size of the resulting hazardous zone.
So good ventilation shrinks the zone.
Absolutely. Good airflow helps to dilute the released substance quickly and reduces the distance over which the concentration remains within the flammable range. The guide really emphasizes the importance of effective ventilation, whether it's natural or artificial, in minimizing the size of hazardous zones.
What else influences the zone extent apart from ventilation?
Things like the properties of the fluid, volatility density, the release rate, the release velocity, and any obstructions that might impede dispersion.
Okay. And we mentioned earlier there's a direct link between the zone and the required equipment category.
Yes, that's the crucial connection. The ATEX Equipment Directive specifies equipment categories, like Category 1, 2, 3, based on the level of protection they provide against ignition. The rule is simple. The higher the risk of an explosive atmosphere, lower zone number, the higher the required level of protection, lower category number.
So zone 0 to 0 needs category 1 equipment. Zone 121 needs category 2 or 1. Zone 222 needs category 3 or 2 or 1.
That's the general principle, yes. You match the equipment's safety level to the zone's risk level.
Our guide even gives specific examples for oil handling, like tanker unloading and tank vents, and also for natural gas. Let's touch on natural gas zoning. What are some key considerations there?
Natural gas, mostly methane, is lighter than air, which affects dispersion. Industry standards, like IGFSR 25 in the UK mentioned in the guide, provide specific guidance. They often treat potential leak sources like flanges or valve glands as secondary grade releases.
Okay.
The extent of the zone 2 around these sources depends heavily on the operating pressure and, again, the quality of ventilation often categorized as high, medium, or low. With very good ventilation and low pressure, the hazardous zone might be deemed negligible extent, or NE, meaning it's so small you don't need specially protected equipment right there.
So ventilation is key for natural gas zones, too.
Absolutely. The guide also introduces the concept of calculating the hazardous volume, V, based on release rate and ventilation effectiveness, although it notes these standard calculations can be quite conservative compared to, say, CFD modeling.
Computational fluid dynamics.
Right? Computer simulations of airflow and gas dispersion, which can give a more detailed picture.
And what about dust zone classification specifics? You mentioned the challenges with settling.
Yeah, defining dust zone extents is trickier than for gases because dust doesn't just disperse, it settles. then it can be kicked up again. So housekeeping becomes a major factor.
How clean the area is kept.
Exactly. Poor housekeeping, allowing thick dust layers to accumulate significantly, increases the extent and severity of Zone 22 and potentially Zone 21. The way work is done also matters. Emptying bags openly creates more dust cloud risk, and thus larger zones, than using contained transfer systems.
So operator practices and cleaning regimes are part of the zoning assessment for dust.
Definitely. And while the dust properties like MIE, MIT, LIT, KE don't directly define the zone boundary, they are critical for the risk assessment within that zone and for selecting equipment with appropriate surface temperature limits, considering both cloud MIT and layer LIT with safety margins.
Okay. This understanding of zoning leads logically to equipment selection and protection methods. What are the core principles when choosing equipment for these zones?
The absolute core principle: select equipment that is specifically designed, tested, and certified as safe for the zone it's going into and for the type of explosive atmosphere present, gas vapor or dust.
Can't just use standard industrial gear.
Absolutely not.
Yeah.
As we said, the ATEX Equipment Directive categorizes equipment, Category 1, 2, 3 for increasing risk zones. When selecting, you need to check: is the category correct for the zone? Is it suitable for gas, G, or dust, D? Is its maximum surface temperature, T rating or stated temp, safe for the specific substances present? What protection method does it use, XNES? And does it have the right ingress protection, IP rating, against dust or water?
That's quite a checklist.
It has to be. Getting any of those wrong could lead to an ignition.
The guide briefly lists some common protection methods for electrical equipment with their X codes. Can you give us a quick flavor of those?
Sure. Some key ones. XI is intrinsic safety limits energy to non-incentive levels. Suitable for all zones, 0, 1, 2, or 20, 21, 22. XD is flameproof enclosure contains an internal explosion used in Zone 121 and 222. XE is increased safety prevents sparks and hot spots in normal operation for Zone 121, 222. XP is pressurization keeps flammable atmosphere out with positive pressure, various zones. XM's encapsulation seals components, all zones. XN is a category for Zone 2 only, less stringent than others. And for dust, XT signifies protection by enclosure, focusing on dust, ingress prevention, and surface temperature limits.
So the code tells you how it's protected.
Yes, and therefore which zones it's suitable for. The guide also makes the point that non-electrical equipment, mechanical gear, also needs assessment, often involving an ignition hazard assessment, or IHA, to determine its category and if specific protection methods are needed.
And IP ratings, ingress protection, how critical are they, especially for dust?
Very critical for dust. The IP rating tells you how well sealed the enclosure is. IP6X means fully dust tight. No dust ingress permitted. IP5X means dust protected. Some dust might get in, but not enough to impair operation or safety.
So which rating for which zone?
Generally, Zone 20 and 21 require IP6X, dust tight. Zone 22 usually requires at least IP5X, dust protected. But if the dust is conductive, you'll often need IP6X even in Zone 22 to prevent conductive dust bridging circuits.
Right, conductive dust adds another layer of risk. Now, you mentioned the ignition hazard assessment, IHA, again, particularly for non-electrical stuff. The guide details this. What's the main goal of an IHA?
The IHA's purpose is to systematically scrutinize a piece of equipment, usually mechanical, but sometimes electrical components too, to identify all potential ignition sources it might contain or create. Then, based on how likely those sources are to become active, you determine the correct ATEX equipment category for it.
So it's a deep dive into the equipment itself.
Exactly. Looking for anything that could get hot, create a spark, mechanical, electrical, static, or otherwise ignite a surrounding explosive atmosphere. It distinguishes between inherent sources, potential sources that need certain conditions, and effective sources likely to cause ignition.
And how does the process work? How do you do an IHA?
Typically, you'd use a systematic approach, often based on a standard list of potential ignition source types. The guide mentions 12 basic types from standards like EN ISO 800-7936. You consider sources within the equipment, like bearings overheating, and also those potentially introduced by the process, like static from flowing powder.
Okay, a structured check.
Yes. For each potential source identified, you estimate the likelihood it could become an effective ignition source during normal operation, an expected malfunction, like a seal failing, or a rare malfunction, like two independent faults occurring.
How do you estimate likelihood?
You consider the design, materials, operating conditions, maintenance, etc. Then you assess any built-in preventative measures. Based on this, you categorize the likelihood for each source, e.g., very high, down to negligible. The guide provides tables to help link this assessed likelihood under different operating conditions to the required equipment category, 1, 2, or 3.
And you need to justify your assessment.
Absolutely. Documentation and justification are key. The final category assigned to the whole piece of equipment is determined by the single ignition source that requires the highest level of protection, i.e. the lowest category number. If even one potential source could become effective in normal operation, it likely needs to be Category 1 equipment.
And the IHA might also specify usage restrictions.
Yes, very often. Things like maximum ambient temperature, suitability for specific gas groups or dust types, maybe limits on speed or load. These restrictions must become part of the equipment's marking and instructions for use. The IHA report itself is a crucial part of the legally required technical documentation for ATEX equipment.
Okay, let's zoom in on some of those common ignition sources the IHA looks for. What are some really key ones?
Hot surfaces are a major one. Equipment getting hot enough to exceed the MIT of a dust cloud, or the LIT of a dust layer, or the TIG of a gas vapor. Proper temperature control and monitoring are essential.
Obvious but critical.
Flames and hot gases, even tiny pilot lights or exhaust streams, are incredibly effective ignition sources. Need to be rigorously excluded or controlled. Mechanically generated sparks are another big concern, from friction, like slipping belts, impact, dropping tools, or abrasion, grinding.
And that thermite reaction risk.
Yes, the guide specifically flags the high risk from impacts between light metals, aluminum, magnesium, titanium, and rusty steel. It can create very energetic thermite sparks, easily igniting most flammable atmospheres. The speed of moving parts is also a factor. Higher speeds increase friction impact energy.
Okay, what else?
Electrical equipment is always considered a potential source, unless proven otherwise through specific protection methods, XD, XI, etc. That's why the EN 630.079 standards are so important. Static electricity, which we've discussed, charge buildup leading to sparks. And finally, stray electric currents, maybe from faulty wiring or induction, causing sparks or heating.
That covers a lot of possibilities. The IHA also considers malfunctions. How does it differentiate between expected and rare ones?
It's generally based on experience, design analysis, and reliability data. An expected malfunction is something known to occur occasionally during the equipment's lifetime, maybe a bearing wearing out, a seal weeping. A rare malfunction is considered much less likely, perhaps requiring 2 independent failures to occur simultaneously.
And how does this affect the assessment?
Category 3 equipment must be safe in normal operation. Category 2 must be safe in normal operation and during expected malfunctions. Category 1 must be safe even during rare malfunctions. The IHA focuses on credible single expected malfunctions and sometimes combinations of expected malfunctions that might lead to a rare event. Highly improbable combinations usually aren't the primary driver for the category, but need consideration.
So the category reflects robustness against faults. All this careful assessment and design work culminates in the marking of ATEX equipment, what absolutely has to be on that label.
Several things are legally required by the directive. You need the CE mark, showing general conformity with EU directives, the specific X symbol, the hexagon, and often the ID number of the notified body involved in conformity assessment.
Okay, the official stamps.
Then the core technical info, the equipment group, I for mining, 2 for surface industries, and category 1, 2, or 3. An indication of suitability for gas, G, or dust, D, the type of protection used, like DIET.
The X codes.
Yes. And critically, the temperature class, T1, T6, or the actual maximum surface temperature in degrees C. For Group 2 equipment, sometimes the gas group, IIA, IIB, or AC it's suitable for, is also marked. Any specific conditions for safe use, often marked with an X, must be detailed in the accompanying documents.
So the marking tells you exactly what it is and how you can safely use it.
That's the intention. The guide references standards like EN 6000790 off for the specifics of electrical equipment marking, and others like EN ISO 800-7936 for non-electrical.
Okay, finally the guide wraps up by touching on the science of fires and explosions themselves. What are the key distinctions here?
It clarifies the difference. A fire is combustion, but an explosion involves a very rapid expansion of volume, usually generating a pressure wave. We're mostly concerned with premixed fuel-air explosions.
And the most common type?
Is a deflagration. That's where the flame front travels through the unburnt mixture at subsonic speed, faster than a normal fire, but slower than the speed of sound. This is what causes the pressure rise in vessels or buildings.
How fast it travels depends on
things like the fuel type, concentration, turbulence. Confinement and obstacles can significantly accelerate the flame and increase the pressure dramatically.
What about detonations?
Detonations are much more violent. The reaction front travels at supersonic speed, coupled with a powerful shock wave. While less common in typical industrial accidents involving vessels, they can occur, especially in long pipelines where a deflagration can accelerate into a detonation, DDT.
And confined versus unconfined explosions.
Unconfined explosions, like a gas cloud igniting outdoors, generally produce lower pressures unless there's significant turbulence, maybe from surrounding structures. Confined explosions inside equipment or buildings are usually much more damaging because the pressure can't easily dissipate. Even mixtures near the LEL or UEL can generate substantial pressure if ignited in a sealed vessel.
So confinement really matters.
Hugely. It dictates the potential pressure buildup and the effectiveness of measures like venting.
So there's definitely more to an explosion than just a loud bang and a flash.
Absolutely. Understanding that science really underpins why all these preventative and protective measures we've spent this time discussing are so incredibly vital.
Well, that was a truly comprehensive deep dive into the world of ATEX and explosive atmospheres. Just to quickly try and summarize the big picture, we've really explored why prevention, stopping those atmospheres forming, is always priority number one.
Absolutely.
We've seen how crucial those thorough risk assessments are for really identifying and evaluating all the potential dangers.
Foundation, yeah.
We've looked at the specific, sometimes sneaky hazards from dusts, and especially static electricity.
Often underestimated.
And the whole logic behind classifying areas into zones, and then the absolutely essential principles for selecting the right equipment with the right protection and the correct marking for use in those zones.
Connecting the risk to the solution.
And hopefully, for you listening, this gives you a much better foundational grasp of what is, let's face it, a complex but really vital safety topic.
Yeah, we aim to pull out the core insights, give you a practical understanding you can use, hopefully, without getting too bogged down in the really dense technical stuff.
So thinking about all those different factors we've discussed, the materials, the processes, the equipment, the environment, it really makes you wonder, doesn't it? What specific areas within your own industry or maybe your specific workplace might warrant the most rigorous, the most ongoing assessment?
That's a great takeaway question. Or perhaps, how could drilling down a bit deeper into something specific, like really understanding the MIE or LIT of the dusts you handle, or mapping out all the potential static generation points, how could that lead to more effective, more practical safety protocols in your day-to-day work?
Yeah, applying this knowledge practically. Lots to think about there.
Definitely food for thought.
Well, thanks so much for taking this deep dive with us today into the complexities of explosive atmosphere safety.
And great exploring it.
We'll be back soon with another exploration. See you then.